Test, test. Let's see if I can get audio. Hey, Andrew, do you mind checking the YouTube to make sure you can hear me? Test, test. Oh, let's see if I can definitely hear me, so that is working. You could hear it? Okay. Well, on YouTube too. Hey, Andrew, do you mind checking the YouTube to make sure you can hear me? Okay, I need to turn that off. Something test. Oh, let's see if I can definitely hear me, so. Okay, LinkedIn. Freaking too loud. Okay. Sweet. Now I know it takes me a while to go set up a live stream. Good to know. Alrighty, so today we'll be covering Deep Reinforcement Learning, Unit 4 from HuggingFace. And this topic, the topic for this week is Policy Gradient with PyTorch. So, let's start with an introduction to policy-based methods. As we know, reinforcement learning is optimizing. The goal of it is to optimize actions to maximize a cumulative reward. So with that concept, we already understand value-based methods where we have a Q table. We try to find optimal Q values, and specifically with deep Q learning, we'll estimate the optimized value of an action, but through estimations. As compared in policy-based methods, we optimize actions directly, not through value estimation. So consider this value estimation as like a second or an intermediary step in value-based methods. In policy-based methods, we go straight to optimizing the actions. And in the course, these are the two environments that we'll be working on in a hands-on environment. We have this cart and pole environment where you go balance a pole on a cart. If you try balancing like a pen on your finger upright, you know that it's hard. Like, oh, you got to make these very small minor adjustments. If you overcorrect, the pen's going to fall. And the same goes in this environment. If you overcorrect, your pole is going to fall off the cart. And this other environment kind of looks like a Flappy Bird, like a Atari style Flappy Bird. And you can see like you're trying to go as far as you can. And you can see like some of the differences in this type of environment compared to what we were doing with a deep Q learning environment. There's a bunch of actions and a huge state. Like this is a continuous environment, especially this Flappy Bird one. You can see like, okay, you could keep on going forever. So are we really going to go estimate? Are we going to take states as an input when this like maybe the amount of states would just keep on going infinitely basically if you can keep beating the game? I don't think so. It doesn't really make sense. That would take up a whole bunch of compute. You'd need infinite compute. So we can see that for this specific environment, maybe it is time to consider using a policy-based method. So let's go dive deeper. What are policy-based methods? So some important concepts. We can do a direct policy optimization, which is finding optimal actions without value functions. Or we can have stochastic policies, where actions are selected based on a probability distribution. The goal is to maximize expected rewards by optimizing policy parameters. So when we were doing deep Q learning, we wanted to get optimal values in our Q table. Like in specifically Q learning without the neural net, but here we will get. We can get these stochastic policies, which give us a probability distribution. So instead of like, oh, I have to do X all of the time with the epsilon greedy policy in value-based methods, like you're always going to just pick the action in that state that has the highest value. But in with policy-based methods, we have access to this new capability, stochastic policies. So say we have, I think maybe in the next slide I might show this. Yeah, I'll just stick to here for now. Instead of like, oh, you must take this action in stochastic policies, we are given options, and we have value, or we have kind of different rewards associated with those actions. And the goal is to maximize expected rewards by optimizing the policy parameters. So the stochastic policy, theta, state, probability distribution of actions at a state with that theta, which is the parameters that we can optimize, use to train our policy. Next, policy gradient methods. Some important concepts here are gradient ascent, which is a technique to adjust policy parameters to increase expected return. There's parameterized policy, which is now a neural network outputs action probabilities. You can see the diagram to the right here, which showcases that. And the objective is to maximize cumulative rewards by tuning policy parameters. So in this diagram, we can see the state. Here are some of the observations we can get from that state. We can get our cart position. We know where what is the cart velocity, what is the pole angle, and what is the pole angular velocity. So we can sense, like, intuitively, this agent will be able to figure out, like, okay, maybe I'm now detecting some pole angular velocity is my current state. It'll go into input layer followed by fully connected layer. So we have our policy with our hyperparameters at that time, at that state at that time, and our softmax, and we have a probability of some certain probability for pushing left and some certain probability for pushing right. So that is policy gradient methods. We're introduced to this reinforced algorithm. So this is the Monte Carlo algorithm. The basic steps for this, just to keep it simple, is we generate an estimate or an episode, we estimate performance gradient, and then we update the parameters. So training episode, you can see that we will go to the end of a training run with this is what generating an episode means. So we'll complete the episode before we go update the parameters. The principle is make rewarding actions more likely in future episodes. So let's just talk about this. This is not there's no real diagram in the course for it, but I just picked this one and we can kind of think through it. So say we start over here. This is a intelligent vacuum, and we're trying to go get dust. If we take certain actions are moving to open spaces. Black you can't go to. You want to go and get the dust. You don't want to go and you don't want to vacuum up these little cute hamsters. So what do? So here we have 3 possible actions. So we would only be able to go up, left, or right. So clearly if we go up, we already get to the reward. And that would be, depending on the objective of this agent, it might just stop there, or it might be going continuously. But the other options are going left. If it goes left, do you have any value, which is kind of the value-based method way of thinking? But in policy methods, you don't estimate a value for that action just yet. You go to the end of the training run. So you go left, then you have to take another action because the training episode's not done. Maybe you go left again, training episode's not done. Maybe now you go up, you get a negative reward. Maybe we say that this concludes the training, and we now know that all of the sum of actions this way is not going to have a good reward, so our policy would be updated, the hyperparameters will be updated, so we know that there's less probability distribution of going to the left because we know that you're not going to get the reward. Similar probability distribution for going to the right as well. So you can see like, okay, go to the right, go up, don't get the reward. So we would then see that like theoretically the probability distribution could be like probability of going up should have like a 99% chance of like as the probability distribution from our agent, our policy-based agent, and the probability distributions for the action of going left and the action of going right would be like very minuscule, like should not be doing it. So that's kind of a reinforced algorithm. And it's with that you can like also infer like these actions are going to be random on the initial episode, so you can like Monte Carlo is just like spamming a whole bunch of trials, and then you can eventually see like, okay, maybe this is the one that we're going to stick with. It's kind of that way of thinking put in layman's terms. So what are some of the advantages of policy gradient methods? You can learn stochastic policies directly. So I'm going to open this up. You can see here that these are probability distributions. So we can turn this into like percentages. So if the wall is up and down, go left has a 50% probability, and if the wall is up and down, you can have a 50% going right probability. They're talking about these two pink areas. So if you're in these states, there's a probability distribution of going left and right equal to each other. So over several different training runs, it'll try going left again, or it'll try going right again in these states. And as a reminder, like we're not calculating the value of the action state pair. We're going to do the full training run and then optimize the hyperparameters to update to get better probability distributions for maximizing our cumulative reward. Some other advantages are they suit high-dimensional continuous action spaces. So it seems like you would be using these policy-based methods for the problem set of like autonomous driving or anything else that has a continuous action space or has high-dimensional actions. Another comparison to draw is like a lot of people have learned like LLM and token generation. Token generation kind of follows that stochastic probability distribution where the next token will maybe has like a 80% like probability of leading to the optimal reward. Maybe like say that you're prompting an AI and you're telling it like, tell me the answer to this math problem I have. Out of all the possible probabilities from the training run that large language model had, you would end up picking up the highest probability. The AI would pick the highest probability token for that specific scenario. And I think, like if you take a look at this environment again, these are very continuous action spaces. Over on this cart balancing scenario, you can continuously move left and right, and like the game, quote unquote, doesn't stop until you don't lose or you keep winning. So those are really the only outcomes. So going back, the other advantage is that there's this natural exploitation handling. So if you look at this diagram and going back to some of the previous units, we talked about the exploitation trade-off. So here, if the model is going to only optimize for the highest possible reward and has more of a exploitative policy, then they'll just keep going and collecting the dust. But suppose that one of these is like an even bigger dust pile. So say this right corner has an even bigger dust pile, which would give much more reward. If you keep on exploiting here, you're never going to go get this big reward that could potentially be here, where just imagine instead of these hamsters, it is like a larger reward. So the hamsters in this scenario are negative reward, but I'm just offering in a scenario where there's potentially more reward here. Because you get that probability distribution, and we will take random actions based on that probability distribution, you may already handle the exploration trade-off, because of the fact, like, say going left and right, there's like a 90% chance to go left, but there's still like a 0.10 chance of going right. You would still, out of 10 out of 100 runs, go to the right with that probability distribution. So from there, you can kind of assume and intuitively see that you're not going to just exploit. There's going to be this probability distribution, and over a large number of training runs, there is going to be this natural exploitation handling. So what are some of the disadvantages of policy gradient methods? They may converge to a local maxima. So depending on the environment, you may kind of like get stuck in this state if the probability distribution is whack. The other thing is that slower, less efficient training, like you saw, you have to go through the entire episode before you optimize your parameters. So because of that, it is going to be less efficient because you have to continue finishing episodes to even try a different set of parameters. So it's slower and less efficient because of that. And there is this potentially high variance in training estimates. More to follow on that, but these are just the high level, what are the disadvantages. And they have a good course on YouTube from Google DeepMind and University College London, or whatever it's called, to learn more about this. I have yet to look into this, but it's recommended in the educational material. Moving on. So let's look at some of the mathematics behind policy gradient methods. This is where my knowledge starts to wane thin because it gets a little complicated. So we have this idea of the objective function, which is the expected return, and it's notated as j of theta. I don't know why it's so small. Let me go get a bigger picture. And just as a reminder, I am currently live streaming this course so that the individuals who are not in the Discord or who want to view it at a later time, can't make this 10 a.m. time hack, will be able to watch it live, but I'll have an updated, edited version coming out shortly after with subtitles, because I know how useful subtitles are. Maybe you're in like a loud environment. There should be no excuse to not be able to learn reinforcement learning. So if there's subtitles, I know that'll simplify the experience. So here's the objective function defined. So we calculate the expected return, the j of theta, by summing for all trajectories the probability of taking that trajectory given theta and return of this trajectory. So that is what this the summation symbol is, and this tau is the trajectory. If you've seen a Monte Carlo simulation before, you kind of intuitively can visualize it. I'd say give it a good look. It's very interesting that random actions can lead to the optimal reward. So very interesting to see. And it kind of shows the power of compute to just really make things fast. Instead of these experiments being slow, just get your GPU on and get the computer doing some work. So the cumulative return is equal to the sum of the rewards, and you can see that this gamma is the discount rate. So that's what this objective function is. And we are now introduced to this policy gradient theorem, which is the foundation for gradient estimation. I know that that diagram is going to be small, so I can pull it up on the course material. So this is the policy gradient theorem. It's a little complicated, but the idea is that we can reformulate the objective function into a differentiable function that does not involve the differentiation of the state distribution. And I'm pretty sure there is a pseudocode example for this. I'm going to go see if I can find it real quickly to cover it. Right here. It's at the top. So this is the pseudocode, like very simply put. It's for each episode, you'll collect an episode with the policy pi, calculate the return, which is the sum of the rewards, and update the weights of the policy. If it's a positive return, we're going to increase the probability of each state action pairs taken during the episode. If negative return, we're going to decrease the probability of each. So say after a training run on this scenario, we get into this state where wall is up and down. So we're talking about these pink states. Like maybe there's just don't imagine there's a reward here. There's just nothing here. So say it goes here and then goes up. Well, I guess it could have a negative reward. That's fine. If we're in this state, we go right and up. The right probability will go down because the return, the reward from that state action is going to be low. Compared to if you're in this state and then you go left and up, it'll be higher. So we would update after this training run. We would see that we got a better return by collecting the dust by going left. So we would update our probability distribution for those state action pairs to something like maybe 70% go left, 30% right, and you kind of iterate that way. You go to the next training run. You do this, you get those same probability distributions, and you see like, yeah, I guess I confirmed that you do get more reward going left than you do going right. So we'll update it again and maybe even have like a 90% go left, 10% go right. So you can kind of see over these training runs, you're going to increase the probability of the actions that will lead to the positive return. And gradient estimation, we use sample trajectories to approximate the gradient. Let's see if I can get it really. This is when it starts to get into the heavy mathematical definitions. And from my experience having worked through / currently finishing up the training run for the last environment, I know that, let's see if it's still running. Okay. I know that this formula, it is like, it's good to understand the backing of it, but when you get a reinforcement learning library, you can just kind of edit the hyperparameters without having to worry about the math. So the level of knowledge I'm trying to get with reinforcement learning, I'm not looking to get into like theoreticals or formula. I'm looking to apply what I'm learning. So I will just kind of rely on my understanding of the reinforcement learning package / library for me to implement this. But if that's something you're interested in, go ahead and take a look at the course for a deeper dive on the definition and what actually is the formula. So now this is the training environment that we are doing for the hands-on portion of the course this week. The goals are implementation of PyTorch and the reinforce algorithm, the Monte Carlo reinforce algorithm. We're going to be using two environments, Cartpole version 1 and the Pixelcopter. And we're going to be following iterative learning by refining the policy through environment interaction. So that's kind of the central dogma of reinforcement learning. You go state, action, reward, repeat. So this is my training run. There's you do both in the course, both the cart pull as well as the Flappy Bird looking one. I forgot what it's called, but I'll just briefly go over some of my findings with it. You can go through this collab notebook yourself at your own time, and I'm just going to go over what I've done so far. I really like these collabs because it really, like, if you just read everything, take some time to digest it, it's really intuitive, and they break things down from scratch. So the goal to get a result of greater than 350 for cart pull and a goal of greater than or equal to 5 for the pixel copter. And for both, I've already went past these minimum thresholds pretty seamlessly. So obviously this time for DeepQ, or not DeepQ, but we're going to be using neural nets. So we're going to use our GPU. You create your virtual display, so you're getting your pre-processing everything, getting a good understanding of what are the libraries we're using. You can see we're importing PyTorch, importing the gem, HuggingFace hub, making sure we have our GPU, and then now the first agent is the cart pull agent. Some of the reasons for using this environment is try have a sign of life on toy problems, validation by making it run on harder and harder environments. So balancing a pull on a cart, having an AI being able to do that, like you would not be able to just code out like if angle is greater than 12, go right, because it's this ever evolving environment. You can tell that when that pull is leaning much to the left, you'll have to have a bigger course correction on your cart to fix it. So this environment is like continuous, and it very, very you can have this theoretically go to infinity, have an agent that's able to just keep going to infinity to balance this stick. So it's a simple environment, but they're putting it in quotes like the sign of life, because that's not something that people can normally do through just a regular hand-coded function, like not using reinforcement learning or deep learning. It would be hard to just go and balance this stick. Alrighty. So you can see that in this environment, we have the cart position, cart velocity, pull angle, pull angular velocity. We have our 2 fully connected layers and a softmax. And the probability, we're going to get the probability of going left and going right. So walking through the material, they kind of throw you for a loop. They show that you need to have the log prob be a tensor data type. So the comparison is over here compared to what you're seeing over in this area. So take a look at it when you're going through it. It's just showing you that you need to have the right data structure. Here's the pseudocode for the reinforce algorithm. You start with the policy, you generate an episode, and then you optimize your policy using this expression. And with that environment, this in total took me 14 minutes to train, and some of the things that you can edit are the hyperparameters. Those are always fun to mess around with. I did a little bit of editing on the training episodes. I did 2000. I don't know what the default one was at this point, but trying out different settings, you can potentially have better rewards. So passing is 350, and you can see that by episode 300, you're already blowing past that. But later on in the training run, like episode 1700, we went down again. So what that means is like the policy actually was updated and made worse. So thankfully we continued training, and then we're getting average scores of 500 every time now. So this agent was, like, you can tell it learned from its mistakes and it got better and improved. So that's the cart pull environment. You go evaluate your agent, and then you can push it to the HuggingFace hub, and then from there you go to this next environment, which I'm now training in, is Pixelcopter. So this is that Flappy Bird looking example. Create a new policy. You define the hyperparameters. This one will have a more complex environment because like the incoming environment, that environment you're traveling is always updating. So this is like a little bit more of a complicated environment compared to the pull cart environment. So there's 7 observations and 2 actions that you can do. You can go up or you can do nothing. And this is a good thing in life to remember. By doing nothing in life, that is an action. You're choosing to do something. So always know that inaction is an action in general. Didn't think we'd be getting all life philosophical in here, did we? But that's when you go through this reinforcement learning material, some of the you'll have these big epiphany moments. I've had a few already. Like, I have a newborn, not a newborn at this point, like a toddler, 1-year-old, 14 months old. And I'm seeing that raising a child is definitely reinforcement learning. You have to, I'm always optimizing for the optimal policy, making sure that my child will grow up to be an effective agent in this dynamic, continuous environment that is Earth and this universe. So go ahead, take a look at the Pixelcopter, update your hyperparameters, and go ahead and train your agent. Whenever you do it, just know that I am only on episode 35,000, and I said that I was going to get to 60,000, and I'm going to keep letting it run. But it is now has been executing for 2 hours and 21 minutes now. So probably it's looking at, I need 4+ hours to go complete this training, because it gets a little bit longer the longer it goes because of it's more complicated. And with that concludes Unit 4, which is Policy Gradient with PyTorch. So recap, policy-based methods. Optimize policy directly for maximum reward. What are policy gradient methods? They use gradient ascent to find optimal policy parameters. What is this concept of balancing exploration and exploitation? This is achieved through that stochastic policy, where you have probability distributions for the potential actions that could be taken at that state. And what are some of the practical considerations for policy-based methods? The training can be slow and prone to local optima. So with that, thank you for watching, and that concludes Unit 4. We're at the halfway point. I went from knowing nothing about reinforcement learning besides going through deep learning coursework on my own, and then going through some NVIDIA training with their transformer-based architecture, which now that I'm going through this material, I should have had a better understanding of reinforcement learning before I go to learning this transformer-based architecture. But you don't know what you don't know, and I'm learning as I go, and I'm going to reinforce the good habits, and I'm going to not do the things that don't give me reward. So thanks for watching. Catch you later.